this video we are going to discuss about the non-ideal IV characteristics of MOS transistor. So on completion of this topic, students will be able to explain the electrical properties of MOS transistor and explain the body effect and its effect in MOS device. So let us see about the non-ideal IV characteristics. So this non-ideal IV characteristics have some behavior. First one is velocity saturation and mobility degradation. Second one is channel length modulation. Third one body effect. Fourth one subthreshold condition. Fifth one junction leakage. Sixth one tunneling. Seventh one temperature dependence. And eighth one geometry dependence. So first one, let us see about the velocity saturation. So here, under strong lateral electric fields that is produced by the drain source voltage, so this charge carriers, when they are accelerated, there occurs some collision between the charge carriers and the silicon lattice, which increases the charge carriers. So beyond a certain level of this electric field, the drift velocity, that is carrier drift velocity, saturates at a particular point, which we call it as Vsat, and this we call it as velocity saturation. So here we can note that the transistor saturation and velocity saturation are two different things, but both of them result in the saturation of current through the channel, and as well as it is with respect to the drain source voltage. So we write this one as E is equal to VDS by L. So here the L determines the length of the channel. So next one is channel length modulation. So channel length modulation is nothing but when we increase the drain source voltage, this depletion region will increases and the channel length becomes very shorter. So the current which is flowing through this channel, that is drain source current, will be inversely proportional to the length of that particular channel. So when we decrease the channel length, the current will increases. So this effect is normally seen in short channel devices when we compare to the long channel devices. So this is entirely different. The regions between the N and the P will have no carriers and the width will grows with respect to this reverse bias. And the next one is body effect. So this body effect occurs due to the, you can see this body effect, source and the body terminals are both connected together into the ground. So if this body is not connected to the source and it is not connected to the different potential, then this causes the threshold voltage to vary according to the formula which is given here, that is Vt is equal to Vt naught plus gamma into pi s plus Vsb minus pi s. So here this Vt naught is nothing but the threshold voltage. So when this Vsb is equal to 0, this eta is the body effect coefficient and pi s is the surface potential. So we can infer that the threshold voltage increases with the source voltage and decreases with the body voltage. So the same thing here in the junction voltage. So junction voltage occurs when there is no current pass through the capacitor. So when we decrease in the thickness between this channel and the gate, so the electrons will constitute the leakage current in this one. So this is reverse bias PN junction. So it has an ordinary diode leakage, band to band tunneling, and gate induced drain leakage. And here this negative diode voltage depends on the doping levels based on the area, perimeter, and totally it is negligible. So you can see the ideal transistor of IV characteristics. So here we have the cutoff region and linear region and saturation region. So in the case of cutoff region, you can see that VGS will be less than VT, and in the case of linear region, this VDS will be less than the saturation voltage, and this in the case of saturation, this VDS will be greater than the VD sat. And here you can see the graph of the ideal plot. So here this IV characteristics determines this channel length modulation, saturation current increases with respect to this voltage, and also this velocity saturation and the mobility degradation will be very less when the current increases or this voltage increases. So here you can see the two equation when the current is in on state as well as in the off state. If the current is in the on state, that is equal to IDS with respect to the gate source voltage, this VDS value will be equal to VDD. And when it is in the, so we say that it's a saturation region. And in the case of off, when the current is in off, which is equal to IDS with respect to the VGS, so this VDS will be equal to VDD, which determines the cutoff region. So here it produces two types of electric field. One is vertical electric field and lateral electric field. In the case of vertical electric field, E vert is equal to VGS by 2x, and in the lateral electric field we determined E lat is equal to VDS by L. And here when high electric field is efficiently produced, it reduces the mobility due to the collision in it. So that formula is given here. And in velocity saturation in IV characteristics, so this is the ideal transistor. So here in ideal transistor, when current is on, it increases with VDD square. So that formula is IDS is equal to mu into COX W by L into VGS minus VT the whole square by 2. So we say equal to beta by 2 into VGS minus VT the whole square. So here this velocity saturated current is on when there is an increase in the current with respect to the drain voltage. And also these transistors are velocity saturated, partially saturated, so that is IDS is since it is directly proportional to the VDD square. And next, the threshold voltage effects. So in this threshold voltage, this is nothing but VGS, for which the channel which starts to invert at a particular point. So that is ideal models that is assumed as here this VT voltage is set as constant. So it really depends upon the weak voltage, and it starts to conduct when there is a change in the VGS voltage, and it occurs due to the body effect, drain voltage, channel length. And next, this effects causes the region to in the linear region. So you can see this in this drain induced barrier lowering. Here the electric field that is from drain, it affects the channel, since this transistors which are closer to the channel. And here this drain induced barrier lowering, which you can write it as VT dash is equal to VT minus eta into VDS. And here this high drain source voltage causes this current to increase. You can see in this graph. And short channel effects. Short channel effect is nothing but in small transistors, see if some drain or source depletion regions extend into the channel, it can causes the amount of charge, that is large amount of charge, to invert the channel. So since this depends on the function of channel length, so this short channel effect VT increases with respect to the channel length. So this can exhibit a reverse short channel effect when this VT decreases with the L. And here in the leakage, so leakage we know if it increases the threshold voltage, or if there is a mobility, there occurs some leakage. So it can leads to cutoff region, or it can leads to linear region, or leads to saturation region. So this leakage sources are mainly due to the subthreshold conduction. So this transistor can abruptly turn either on or off, and also it has a dominant source in contemporary transistors. In the case of this, it occurs in the subthreshold conduction. So in case of gate leakage, there is a tunneling through the ultra thin gate dielectric, and in the gate junction leakage, there is a reverse biased PN junction diode current. Next is the subthreshold leakage. So in the subthreshold leakage, this is mainly due to the change in the gate source voltage, so that we can written as IDS is equal to IDS naught e power VGS minus VT naught plus eta into VDS minus K into VSB by eta VI into 1 minus e power minus VDS by VT. So this is given in the, that is IDS, it is rewritten on the log scale as IDS is equal to I of into 10 VGS plus eta VDS minus VD by S minus K eta VSP into 1 minus e power minus VDS by VT. So in this gate leakage, so you can see in the gate leakage, it occurs due to the that is the gate and the channel forms a capacitor. So here no current can pass through the capacitor ideally, but with the decrease in the oxide thickness between the gate and the channel, this electrons tunnel across this constitutes a gate leakage current. So from this graph you can see that the gate leakage increases by a factor. So this is about 220, and also this, to keep this gate voltage below the level, this oxide thickness must be at least greater than 10.5. So this gate leakage current can be reduced by substituting the silicon dioxide with a higher dielectric constant material. And the next one is band to band tunneling. So here this tunneling occurs mostly in heavily doped PN junctions, especially it occurs in the side walls between this drain and the channel. So this increases the threshold voltage. Due to the increase in the threshold voltage, it increases the junction leakage. So that we have written here the equation. So here this gate induced drain leakage which occurs at the overlap between the gate and the drain. So here most pronounced when you are using this is drain is at VDD and gate is at negative voltage. So this efforts can reduce the even a small point of the threshold leakage and also the negative gate voltage produced in this. So that it is given in this graph, we can reduce the subthreshold leakage which is present in the negative region. And next one is temperature sensitivity. So this increases the when increasing the temperature reduces the mobility and reduces the threshold voltage. When this current is on, it decreases with the temperature, and when it is in the off state, it increases with the temperature. So that is given in the graph. And next is, so what if transistors are not idle? What happens? They still behave like switches, but these effects matter for only for supply voltage choice, logical effort, and power consumption, pass transistor, and temperature of operation. So quiz questions on the non-ideal IV characteristics. Derive the noise margins for CMOS inverter. Thank you.